Hello. Let's see. Hello, this is Solutions for Homework 4A, and let's begin with problem 1. Problem 1 talks about projectile motion, and specifically, it gives you the launch. It says that the launch speed of a projectile is 3 times its speed at maximum height. So let me draw a projectile. So that's a simple projectile. That could be the ground, and the launch speed means the velocity. Oops, let me redo that. So that's your velocity vector, right? The velocity with which you launch the projectile. So that's we have been using the notation v initial for that. That's a magnitude of the total speed. That means the magnitude means the x component plus the y component. It makes an angle theta initial with respect to the horizontal, and which can be immediately broken into. Let me use some colors here. So maybe blue. So that's your x component, and the y component can be in red. So the y component is v initial y, and the x component is v initial x. Now, the nice part of projectile motion is that the x component is not accelerating. That means its velocity stays the same in the horizontal direction. Everywhere it stays the same. Even while it is right on the top, this stays the same in length, and that represents that. The the y component instead keeps decreasing, so it decreases in size, it gets smaller, it becomes zero right here, then start accelerating downward, right? And at this point, it will be something like this. Now, what is given to us is the V initial piece in here. So before I begin, let's say, let me write down a few things. So notice that V initial in the x direction is equal to V initial, or the x component of the launch speed is equal to the launch speed itself times cosine theta initial. That's a vector relation if you want. But since the x component remains the same right when the projectile is on the top of the trajectory, it has only one component, and that's equal to v initial x itself. So what have they given us? So we have been told that the launch speed of the projectile is 3 times its speed at maximum height. So what is given to it is the launch speed is v initial is equal to 3 times its speed at maximum height. So 3 times, what is the speed at the maximum height? That's v initial x. So that's v initial x. The x component remains the same, and right when it is on the top of its at the top of the trajectory, it is just purely x component. Y goes to 0. So that's what is given to us. With that information in, we can actually substitute this in here. So that's equal to 3 times v initial x times cosine theta initial. The first line is a vector relation, and second line uses this given feature that allows us to cancel v initial x, and we get 1 is equal to 3 times cosine theta initial. And immediately we can calculate the launch angle now. This implies that theta initial is equal to cosine inverse of 1 over 3. You divide out by 3, and that allows us to calculate the launch angle. That's equal to calculator. So I get, so it's cosine inverse of 1/3. And that's 70.53. So let me, so there's, it's not very clear how many sig digits are there, because we are only told that it is 3 times its maximum height. So it's a, uh, it's not very obvious what's the significant digits here. So let me write 3 sig digits here, and that's 70.5. It's more of a theoretical problem. So when they say 3 times, it's 3.0 or is it 300? So it's given in words. So the sig digits is not very obvious in this problem. So that's problem 1. Let me pause for a minute here. So this is problem 2 in homework 4A. It's similar to problem 1, but now we are talking in terms of project, the range and height of a projectile. Again, if we have a projectile that looks something like this, very rough picture, and it starts and ends at the same level in as far as the vertical height go, and the range is the horizontal distance r, and the vertical distance here, that's your height of the projectile. And we have nice relations for this. The range is given in terms of initial launch speed. So that's a vector v initial, and that's your theta initial. In terms of that, we have the initial square times sine of 2 theta initial. Remember that the maximum is attained when initial angle is 45 degrees, and that's the characteristic of that sine of double angle, and divided by g. On the other end, the horizontal, the vertical height, maximum vertical height, is given again in terms of the square of the initial launch speed times, instead of sine of double angle, it is sine of the angle itself squared. So that's sine square theta initially. You can think of it as sine of theta and then squared in that manner, and divided by 2 times g. Right? And we derived this in the class. Now, what is given to us is that the range of the projectile is 3 times its maximum height. So given the range is 3 times h. Right? And we have to find the launch angle. So substitute these equations in here. So that's v initial square sine 2 theta initial divided by g. That's equal to v initial square sine square theta initial divided by 2 times g. The cancellations in here. Oh, you have to put in 3 times, right? So it's just 3 times. That's a condition that comes in. V initial square cancels out on both sides. G cancels out on both sides. And we also have expand out the sine of a double angle. So that's 2 times sine theta initial times cosine theta initial. That's equal to 3 by 2 times sine square initial. One of the sine theta again cancels out. So what we are left out with is we can think of again divide out by cosine theta. That makes it a tangent theta. So we have 4/3 is equal to tangent theta initial. I've taken the 3/2 to the left hand side and brought the cosine theta to the right hand side. So that makes it a tangent theta on the right side and 4/3 on the left side. So that lets me calculate the launch angle. That's tan inverse of 4/3. And that's equal to, use the calculator. So that's 53.1. Again, the sig digits is not very clear here, because when in the problem I have told you it is 3 times, it is not given whether it is 3.0 or it is 3.00. So that decides the sig digits here. So it's ambiguous there. So let's just report it with 3 sig digits. So it's 53.1 degrees. And of course, when we give an angle, we should always say it is with respect to the horizontal, but in the projectile motion, it is clear the launch angle is with respect, that's defined with respect to the horizontal in the counterclockwise direction. Let me pause here again, and I'll come back with problem 3. This is problem 3 in homework 4A. Again, it's a projectile motion, but this time it is a half of a projectile motion. So what it talks about is we have a floor. That's, let's say that represents the floor, and this is a table. Let's say that's the edge of a table, and a mug apparently, or a mass has been is is a student slides a mass off the top of a horizontal table. So it's expected to go horizontally in the initial point, and then takes a projectile motion. And right in the initial point, its velocity is horizontal. So that's v initial, and it is in the x direction purely, right? That's v initial x. The height of the table is 1.3 meters. So it's 1.3 meters. And the mass slides off the table with a horizontal speed of 3.50 meters per second. And how far from the base of the table does the mass strike the floor? So we have to calculate this delta x, right? So that's this distance here. It's very similar to the package dropped by an aeroplane that we worked out in class in the morning today. So let's do this slowly. Let's figure out what are the quantities given so that it helps with other problems too. So the parameters usually in a projectile motion is delta x, delta t, and v initial in the x direction. Other velocities, the final velocity doesn't come into picture because it stays uniform, and acceleration is 0 in the x direction, right? Delta x, delta t, and v initial x. And in the y direction, we have delta y, delta t, v initial in the y direction, v final in the y direction, and acceleration in the y direction. In the y direction, it is accelerating downwards. It's a choice whether we choose the positive direction to be up in the upward direction or downward direction. So let's choose our positive to be positive in the upward direction. And horizontally, the positive direction is towards the right. So that immediately tells us that this is minus 9.8 meters per second square, because it's falling under gravity. Why 9.8? We will get to know that later in the semester. What are we asked to calculate? Delta x, how far does it go? So that's the quantity we are looking for, delta x. Delta t is not known, but it is common in both the x and y direction. We have split the problem purely in the two orthogonal direction. V initial x is plus 3.5 meters per second. But if we want to calculate delta x, we need to know delta t, which is not immediately available to us. So we look for in the y direction. What else is given in the y direction? 1.3 meters. That's the vertical distance the ball travels from the initial to final point that's being considered. And since we said positive direction is going to be in the upward direction, this is going to be a minus 1.30 meters. So final minus initial, so however you measure it, final point is at a lower point than the higher point. If these two is positive to be in the upward direction, that gives us minus 1.30 meters. We initial y, now notice that in the initial point, the mass is moving horizontally, so it has no y component, so that's equal to 0. And that's the information that is given to us. And the strategy is we are interested in delta t, so try to find out delta t in the y direction because we have three information given to us. And once we have the delta t known, then we can use two of the quantities given and we can calculate delta x. So that's going to be the strategy. To calculate delta t in the y direction, we need to have an equation that does not have v final velocity because that's what is missing in a sense. So that's missing. So we look for the kinematic equation that does not have the final velocity, and that comes out to be delta y is equal to v initial y delta t plus half times acceleration times delta t squared. Delta y, solve for delta t in here or just plug in whatever we know. So that's minus 1.30, dropping the units. The initial y is 0, so nothing in there's no point in multiplying delta t there. Plus half acceleration is minus 9.8 and delta t squared. The negative sign on both sides cancel, and this allows me to calculate delta t. That's 1.30 into 2 divided by 9.8. And that comes out to be 0.26. Since 9.8 has two sig digits, so I'll have 0.27 seconds. So since the height is so small, the time taken is really tiny. So now we know time, so that's 0.27 seconds. And that means that this is also 0.27. So once we have the time, we can actually use there's only one equation in the x direction. So we have delta x is equal to velocity times delta t, right? Standard uniform velocity formula, and delta x is the initial x is given to us, so that's 3.50 times delta t, which we have already found now, so that's 0.27. And since we are working in meters second and kgs, all these units cancel out, and we get 3.5 into 0.27. So that's 0.945. So it's 0.95 meters. So it's about 1 meter there. So it starts from 1.3 meters and it goes about 1 meter horizontally. So let me stop here and let me get back. This is problem 4 in homework 4A. We again have a projectile motion, but in the problems 3 and, or at least in problem 3, we were having a half projectile, but here we have the following situation. So this is the floor or the ground, let us say, and this is a roof of a building. So that's a roof of a building, and we throw the ball from this height, right from the edge of the roof, and it is thrown at an angle of 30 degrees. So 30 degrees is slightly small, so that's the reference, and that could be the motion of the or the path of the projectile motion. That's a reference line with respect to the roof, and what we are told is this is angle, this velocity, the launch speed v initial makes an angle of theta initial that's 30 degrees, and this is equal to 10 meters per second. Right, that's the information that's given to us. So the height from where it is thrown is 45 meters, so that's 45 meters. And we are asked to calculate how long does it take for the ball to reach the ground. So again, let's collect what are the quantities given to us. X direction, we have delta x, delta t, and v initial in the x direction, right? So v initial in the x direction is, let me first write down the y also. So y is, these are the parameters that's typically of interest in a projectile motion. So v initial in the y direction, v final in the y direction, and acceleration due to gravity, which is minus 9.8 meters per second square, where we have chosen the positive direction to be upward vertically, and positive in the horizontal direction is to the right. Okay, so what are the quantities given to us? 45 meters is the distance traveled between the initial and final points. Where is the initial and final point? That's your initial point where it is launched, and right before it touches the ground is your final point. Right? And the displacement in the y direction is 45 meters, but it is downwards, so it's minus 45 meters. Delta t is what we are looking for. V initial in the y direction, we have the magnitude and the angle given to us, so we can calculate both the x and y component. The x component will be V initial cosine theta, so that's 10 meters per second times cosine of 30 degrees. And that's 0.87 here, or into 10, so that's 8.7 meters per second. So cosine 30, that's 0.866, so that's 8.7 meters per second, right, to two digits. Again, it's positive because it's horizontally in the positive direction, or horizontally to the right, if you want. V initial in the y direction similarly is again vertically upward. So it's plus 10 times sine theta, which is sine 30. Sine of 30 is half, so that's exactly 5 point. So it's plus 5.00 meters per second. Later in the problem, we are asked what will happen if this was thrown downwards, and the difference would be that this sign would change. Right? Instead of positive, the vertical component is negative. Horizontally, it is still stays 8.7 meters per second. We are interested in the time. So it seems like we have three quantities in the y direction given to us, so we can calculate time. So delta t, we don't even have to explore the x uh, side at all. And v final y is the missing variable. That means that's not being addressed at all. And the equation turns out to be delta y is equal to v initial y times delta t plus half a delta t square. Substitute in the numbers, delta y is minus 45. If I keep meters, seconds, and kgs typically, but mass is not coming into picture in these chapters. So we can drop the units and bring it back whenever are, we want to. The initial y is plus 5, so it's 5.00 times delta t, and plus half times minus 9.8 times delta t squared. 9.8 divided by 2 is 4.9. With a minus sign, I take it to the left-hand side. So that's 4.9 delta t squared minus 5.00 times delta t minus 45 is equal to 0. That's 45.0 actually. So it's 3 digits. But 2 is sufficient because 9.8 is only 2. This is a quadratic equation and we can immediately solve for this. So delta t will be plus 5.0, so minus of b, plus or minus square root of 5 square, negative 5 square if you want, minus 4ac, so that's minus 4 times 4.9 times minus 45. Divided by 2 times 4.9. So that's equal to, let me calculate the square root separately. You have, it's a positive quantity because the second term actually has a 2 negative signs in there. So it is 45 into 4.9 into 4. So that's 882 plus 25. Oops, mistake here. So 45 into 4.9 into 4 plus 25. That's 907. So that's 5.00 plus or minus 907 square root of that. That's 30.1 if you want. So it's 30.1. You need only 2 digits divided by 9.8. So that's equal to, there's a positive and a negative number in there. So 30.1 plus is 35.1 divided by 9.8. So that's 3.6 seconds. So plus 3.6 seconds. All. And you can also have a negative, right? So that's 25.1. And I subtract it. So 25.1 divided by 9.8. That's minus 2.6. The time when it hits the ground is going to be positive. That means it's going to be in the future. So that's the correct answer. That's your answer. At least that's the answer to the first part. Now they ask you, how will your answer change if the stone is thrown downward at an angle? So now see the changes that will happen. Let me use a red color for this. When you throw the ball downward, the same thing is happening here. So the trajectory is downward, like this. And if you notice, that is exactly symmetrically, if you were to displace this red line over to this point here, that is same as the old trajectory. If you were to remove that point where it goes up and then reaches the reference line of the roof. So that's the problem that we are addressing, right? So that's 10 meters per second this time, and that's 30 degrees. What changes in that case? The most of things remain the same, except that the v initial y now has a negative sign, which I write on top. That goes in to your equation, and you get a negative sign here. Earlier, this was positive. So earlier, this was a positive sign. You get a negative sign here. When I move it to the left, this becomes plus. What changes? Let me again write the original one to be plus here. So this makes it minus now. And if it is rest, everything remains the same. There is a negative sign in here, but that's going to be squared, so that doesn't change. So again, this becomes a minus. And originally we had the positive sign. And the only difference that is going to happen is that now there are two answers. There is -5 minus, if it is -5 minus 30, so that's 35. So there could be minus 3.6 seconds. So let me see, there are two answers now. This is part B, let's say. So this could be minus, let me put it in red. Undo and red. So this will be minus 3.6 seconds or plus 2.6 seconds. And this time the answer is the positive quantity, and that's plus 2.6. It's also good to see that the negative 2.6 in the first condition that we got, that is the same as the time it takes if it were to go backward. So if it were to go backward here, right, that's equivalent to the same red curve that is symmetrically onto the opposite side. So you can either say it is a time taken for the red trajectory or the black trajectory when it is going backward, or starting from the red dot here and going forward. All those have the same time involved and the various interpretations. But here we are talking about the red curve. That's the actual physical picture we have in mind. There is a symmetrical relation between the other 3 points that I talked about. That completes problem 4. Let me pause here and I'll come back. This is problem 5 in homework 4A. And it talks about a football being kicked and whether it will clear the goal or not. So let me draw a diagram describing the problem. So we have, that's the ground, and at one edge we have a goal which is about 3 meters high. So let me show that. So that's, oops. So that's the goal. And the football itself is kicked from a certain point here. And the question is it going to clear the goal or not? Let's pretend that this is the point where it reaches. So this is the point we would like to know. And if that height is below the height of the goal, then it doesn't clear it, and we have to see, we have to analyze whether it is above or below. We are given the initial velocity here, so that's your velocity that's given to us. So that's v initial, and that's equal to 20 meters per second. And the angle at which it is launched, it is 40 degrees. The distance of the goal from the place where it is, where the football is kicked, is 36 meters. So this distance is 36 meters. And delta y would be this height. Delta y is here. But this distance is given to us to be 3.05. So we would like to calculate delta y and then find out if it is larger than 3.05 or less than 3.05. So let's again list the quantities. So we have in the x direction, delta x, delta t, and v initial in the x direction. Delta x is plus 36 meters. Delta t is not given. V initial x will be 20 meters per second times cosine of 40, because the angle is with respect, angle is in the first quadrant if you want to imagine that as a vector. And that's equal to cosine 40 times 20. So that's 15.3 meters per second. So it's plus 15.3 meters per second. Since later we will have only two sig digits because G is given in 9.8. So eventually we can break, this third digit will not be relevant. In the y direction, we have delta y. That's the quantity we are interested to calculate. Delta t is not given to us, but that's the same delta t as we have for the time evolution, is the same for x direction and y direction. The initial in the y direction is equal to plus, because it's launched upward, it's plus 20.0 times sine 40, which is equal to 20, no, sine of 40 again into 20. That's 12.9 meters per second. Again, I've kept third digit, but it's not relevant. Eventually, we have to keep only two sig digits because acceleration due to gravity is known to only two sig digits. V final in the y direction, when it is right at the, while it is crossing the fence, what is its velocity, y component of the velocity is not given to us. Acceleration due to gravity is minus 9.8 meters per second square. So strategy is going to be, again, we need three quantities to calculate delta y. So calculate delta t from the x direction, then use that same delta t because that's common in the x and y direction. And once we have three quantities, we can actually calculate the delta y, how far it is. So let's start with the x component. So it's delta x is equal to the initial x times delta t. So that's 36.0 is equal to 15.3 times delta t. And that gives the delta t to be equal to so that's 2.35. So let me keep two sig digits now. Or let's still keep threes, because G has not yet come enter the game here. One can argue that as far as time calculation goes, I know the time to three sig digits, even though later on the distance might not have three sig digits. Once I have delta t, so this, I write this down here, 2.35 seconds. It's 2.35 seconds. And the vertical distance traveled will be given using a formula that does not have the final velocity. So that's again the initial y delta t plus half a delta t square. That's equal to plus 12.9. So it's plus 12.9 times 2.35 plus half of minus 9.8 times 2.35 square. And that leads to 12.9 into 2.35. That's about 30.3 minus of 2.35 square into 4.9. So that's 27. So that's known to only 2 sig digits. So that's 27. So that leads to a calculation of 3.3. Meters. And in here, this could be a little sensitive because even though I'm given 3.05 meters, that's not really relevant because it could be 3.0 or 3.1. The third sig digit really doesn't play a role because acceleration due to gravity is known only to 9.8. But nevertheless, I know that it has gone all the way to 3.3, so it does clearly get out of that error bar. So, so remember delta. So how much does it clear by? 3.3 minus of 3.05, which could be, please again, this could be anywhere between 3.1 to 3.2. That's okay because either way, this is positive. So this is equal to 3.3 minus 3.1, let's say. So it's 0.2 to 0.1, anywhere between that. Either way, it clears that. So with an error bar, you would say this is 0.2. Meters. It could be 0.1 also. Whenever we say 0.1, it's understood that it is plus or minus 1. So it does clear. By how much does the ball clear or fall short of clearing the crossbar? So it is plus 0.2 meters. It's a little sensitive at the end point, but it does clear off within the error bar. So let me pause my recording here. This was problem 6 in homework 4A. This talks about a projectile motion related to when a rifle is aimed at a bullseye and how the bullet misses the target by a certain amount. So let me draw a diagram for this. So this is a, let's say, let me not draw that. So this is a reference line. Straight horizontal line there. If a bullet is shot with a velocity, it actually travels along and tries to drop. Oops, it's too much. Okay, drop. So this is tries to drop there. I don't mean to say this seems to be too exaggerated. Yes, that's and that's the amount of fall it makes. So this is delta y. This is very similar to the problem we had with a package we dropped from an aeroplane, and we started on this problem in the class today in the morning. So a bullet has a very high speed, and it's given that its v initial velocity, which is purely in the x direction, is 750 meters per second. The delta the x that it travels, so that's delta x, horizontal distance that it strikes is what we have to find, and the vertical distance that it falls, the delta y, is given to be 0.25 meters. I think that's the quantities that is given to us, and let's list them here. So x direction, we have delta x, that's what we are interested in finding. Delta t, we don't know. V initial in the x direction is 750 meters per second. In the y direction, we have delta y given to us to be minus 0.25, so that's crucial. So it's minus 0.25 meters. Again, choosing everything to be positive in the upward uh, direction when it comes to y. Delta t is common to x and y, but we don't know that. We initial in the y direction. The initial point is right when the bullet is leaving the rifle. That's initial point, and that's your final point. At the initial point, the velocity is purely in the x direction. That means its y component is 0. That's a concept. The final velocity in the y direction, that is when it reaches the target, we don't know that. And acceleration due to gravity, the bullet actually falls under gravity. That's minus 9.8 meters per second squared. So again, strategy would be to calculate delta t in the y direction, then use the same to denote the time in the x direction also, because that's common. And once we have two quantities in the x direction, we can calculate delta x. Again, it's coming out with the same equations. The final y is missing, so delta y is equal to v initial y delta t plus half a delta t squared. It's almost identical to the problem 3 that we did, where a student was sliding the mass off a table. So at least the strategy wise it's the same, but the storyline changes and the interpretations change. Delta y is minus 0.25 meters. V initial y is 0. We have half times minus 9.8 times delta t squared. Delta t is equal to delta t is equal to the 0.25 into 2 divided by 9.8. So that's 0.051. Then we have to take a square root of that. That really makes it small quantity. So that's 0.226. So 226 is 23 because there's 9.8. So we have 0.23 seconds. Let me check this again. 0.23 square into 9.8 divided by 2 should give me 0.25. Yes, let's get 0.26. So that's a reasonable number once we have delta t. So that's 0.23 seconds. That's 0.23 seconds. We can actually calculate delta x, how far it is. That's v initial x times delta t. So 750 times 0.23 seconds. So that's 750 into 0.23. And that's 172.5, and keep to 2 sig digits. So that's 170 meters. So the rifle uh, is 170 meters from the target. At this point, while I'm doing this, it strikes me that maybe I forgot to take the square root in problem 3. So let me go back and try to see that. So problem 3. So let me check if I did that calculation correct. So 1.3 into 2 divided by 9.8. That's equal to 0.27, but I'm supposed to take a square root of that. So there's a small error in this number, so let me correct this. So that's not correct. So that's 0.52 seconds. So that's 0.52 seconds. And that's 0.52 seconds. All right, let me check again. 9 into 0.52 square. That's 1.3, yes. So this is not 0.27, so it's 0.52. And so it's 3.5 into 0.52. So that's 1.8 meters instead of 0.95 meters. Hopefully this error doesn't confuse you guys too much, because you will see this error only if you go through the whole video. But hopefully it is not too damaging. Okay, I'll stop here. Good luck and all the best.